Hello, and welcome to your first causal inference lecture. The first thing I want to talk about today are DAGs. Now, we talked a little bit about DAGs in the context of graph theory before, but now I want to talk about them a little bit more in the context of causal inference. So you may remember that DAG stands for a directed acyclic graph. Directed just means that all of the edges in the graph have a direction. They go from one node to another node. In the context of causal inference, the edges look for causes. So if we have an edge going from one node to another, that means that we think that that node causes the second node. DAGs are also acyclic. Acyclic means that there's no cycles in the graph. Remember, a cycle is a path that doesn't repeat any nodes or any edges, that goes from one node all the way back around to that node. And the reason that this is really important in a causal inference DAG is because that would mean that a variable could actually cause itself, which would not allow us to actually figure out what causal effects there actually are. Last but not least, of course, you know that a DAG is a graph, which means that we have variables represented by nodes and edges which represent causes that flow between the variables. Now, DAGs don't specify any parametric assumptions about the relationships. This means that we just think there is a relationship, but we're not making any assumptions about how strong the relationship is, if it's positive or negative, whether it's linear or nonlinear. We just know that there is a relationship that exists. So why are DAGs important? Well, let's look at a really silly example. It turns out that the number of people who drowned by falling in a pool is really highly correlated with the number of films that Nicolas Cage appeared in. One DAG that could explain this relationship is one that looks like this, where we have the node for Nicolas Cage on the right causing the drownings on the left. One of the things that we're going to talk a lot about in our causal inference section is the fact that DAGs are really important. If our DAG is not valid, then neither are the causal estimates that we get from our models. So what do you think? Do you think that Nicolas Cage being in movies is actually causing people to drown by falling in a pool? Or maybe is this DAG a little bit more reasonable when we add a third variable, summertime, that causes both drownings in pools and Nicolas Cage movies? To me, this seems like a much more reasonable DAG that explains the relationships between our variables. But one of the things that you'll find with causal inference is that you can't just tell statistically what the correct DAG is. You often need outside expertise, whether it's from a subject matter expert or even just from yourself, like the fact that we really don't think that Nicolas Cage being in movies is causing people to drown. So when it comes to DAGs, there are three core paths that we'll need to be able to pick up on in order to estimate causal effects. One of them, the fork, is what we just saw. In a fork, we want to know the relationship between variables x and y, but there's a third variable z that is acting as a confounder. Essentially, z causes both x and y, and so it makes it look like there's a relationship between x and y when really all that's happening is both of them are caused by z. All right, let's talk a little bit more about forks specifically. Now, the fork pattern looks a little something like this. However, forks can actually be subgraphs in much bigger DAGs, so we're going to learn about them in more simple cases, and then we'll expand to more complicated DAGs. So a fork basically looks like what the name implies. In a fork, there is a confounding variable z that causes two other variables x and y. A simple example would be where x is umbrella usage, y is sprinkler behavior, so whether people have their sprinklers on or off, and z is the rain. Now, if we just observed data, we might think, or we definitely would see, that umbrella usage and sprinkler behavior are associated, because when one happens, the other tends to happen. However, we know, just based on common sense, that these two things aren't causing each other. When people turn their sprinklers on, it doesn't mean that people are going to have widespread umbrella usage and vice versa. But we do know that there's a third variable, rain, which affects both whether people are bringing umbrellas and whether they have their sprinklers on. Another example is where X could be annual income, Y could be test scores, so cognitive test scores, and Z could be years of education. We don't think that raising your annual income is going to increase your cognitive test scores, but we do have a third confounding variable z, the number of years of education that you've had, that might influence both your annual income as well as how well you can score on cognitive tests. So let's look at some simulated data that can help us see why fork patterns can cause a problem. So let's say that we're interested in the question, similar to the example before, of what is the impact of cognitive testing on your annual income? So what we're going to do is we're going to simulate some data that has relationships that we know and see how different forms of models might help us get the right or even the wrong answer. So here in this code snippet, you can see that we're simulating data where annual income depends on the number of years of education that you have, and cognitive test scores depend on the number of years of education that you have, but they are not directly causing one another. Because we're simulating the data, we also know what the exact coefficients that a linear regression model should estimate are. In the case of the impact of years of education on cognitive testing, it's 2.4. In the case of years of education, its impact on annual income, it should be 1,500. So let's take this simulated data and plug it into just a basic linear regression that has annual income as our outcome variable and cognitive test scores as our predictor variable. Now, because we simulated the data, we know that the effect of cognitive test scores on annual income is 0, because when we generated annual income, we didn't use any information about cognitive test scores. However, our linear regression model says that there is a statistically significant positive coefficient for cognitive test scores. It says that every time cognitive test scores increase by 1, we expect your annual income to increase by, about $85. Now, it might be tempting if you've ever done a model like this to interpret the coefficients causally. In this case, we might say that cognitive tests increase your annual income. But based on what we know about DAGs, we know that we might have to be a little more careful in our interpretation of this coefficient. Remember, in this case, we happen to know that cognitive test scores and annual income are not related at all. We can tell that because the DAG has no arrow between X and Y. They do not cause each other at all. But we do see that there's a confounding variable, in this case years of education, that causes both X and Y. The word confounding is really useful here because it tells us that the presence of Z is causing an association between X and Y that's not causal. So how do we handle it? Are we just screwed? The answer is no. When we have a fork pattern in our DAG, we can get rid of that non-causal association by controlling for the confounder. In other words, we're going to look at a model that has not just cognitive test scores as a predictor, but also years of education. People often refer to this as controlling for years of education. And you can see that when we have a model that has both our predictor, cognitive test scores, and the confounder, years of education, we get a much more accurate estimate of our causal effect. You can see here that our coefficient for cognitive test scores is very, very close to 0, which we happen to know is the correct answer. Thus, if we have a fork pattern, controlling for the confounder allows us to get a causal estimate of the impact of cognitive test scores on annual income. So, in conclusion, if we see a fork pattern, we want to control for the effect of the confounder if we want to get an accurate causal estimate of the impact of X on Y. Now, one of the ways that we controlled for a variable was just adding it as a predictor to a linear regression. But in the next class, we'll talk a little bit more about different ways that we can control for variables. All right, let's talk about the next common path in DAGs, which is a chain. A chain is exactly what it sounds like. It's 3 or more variables where our first variable X has an effect on Y, but only through changing the variable Z. For instance, we could say that X is hours of studying, Y is exam score, and Z is your comprehension of material. Now, studying more probably impacts your exam scores. Those two things are probably associated. However, studying only impacts your exam score through increasing your comprehension of material. If you studied the wrong chapters or studied in a way that's really inefficient for you, you're not going to increase your comprehension of the material, and therefore your exam score will probably also not increase. Another example could be something like the effect of diet quality, improving your gut microbiome, which then improves your mood. It's not that your diet quality per se has a direct effect on your mood, but if it improves your gut microbiome, that might have an improvement on your mood. Let's look at an example of this. So here we have that gut microbiome example, and again, we're simulating some data so that we know the answers, so we can see how models perform in different circumstances. Here we're simulating a small data set of diet quality, microbiome, which is caused by diet quality, and mood, which is caused by microbiome. Our question is, does diet quality impact mood? We expect that the total effect of diet quality on mood is going to be the product of the coefficient of diet quality on microbiome times the coefficient of microbiome on mood. In other words, 2.5 times 2, or 5. When we build a linear regression, if we just regress mood on diet quality, we in fact get an estimate very near 5. However, should we interpret this coefficient causally? It's actually kind of a difficult question. So one way we can look at this is to ask, if we increased your diet quality, what would we expect to happen to mood? And in this case, it seems like we would expect your mood to improve if we increased your diet quality. Now, what would happen if we controlled for microbiome? In our fork example, controlling for our third variable Z actually helped us get a better causal estimate. Let's see if that's true here. As a side note, when we say that we're controlling for a variable, what we really want is the effect of X on Y after accounting for Z. Covariates in a linear regression model are just one way to do that. In other words, we're asking the question, if we already know what the values of Z are, how does adding information from X impact Y? In this case, if we add microbiome as a covariate to our linear regression model, we're asking, what is the effect of diet quality if we already account for the effect of microbiome? Now, I want you to pause before I move to the next slide and think about what you think will happen in the model when we add microbiome as a covariate. So this is what happens when we look at the effect of diet quality on mood after accounting for the effect of microbiome. We get a very near 0 coefficient estimate of diet quality, meaning that if we already account for the effect of microbiome, diet quality has very little impact on people's mood. And that makes sense because we generated the data and we know that that's true. Since diet quality only affects your mood through your microbiome and not directly, then if we already account for microbiome, there should be little to no effect of diet quality itself. So what do? It actually depends on the situation and what you're trying to estimate. In the context of a chain, we call Z a mediator of X on Y. This means that X's relationship with Y only flows through our third variable, the mediator, Z. For chains, we do not want to control for mediators if we want to get an indirect causal estimate of the effect of X on Y. For instance, if we wanted to know, how does changing your diet impact your mood, even if it's through another variable, then we would not want to control for that third variable, microbiome. However, for chains, we do want to control for mediators if we want a direct causal estimate of X on Y. In other words, if we want to know how independently X causes Y, absent of its path through other variables like microbiome, in that case, we do want to control for other mediators, just like we did. Now, when we have chains, we might not have a direct arrow from X to Y, or we might also have a direct arrow from X to Y. Here's an example of what a chain would look like in this context. For instance, X might be caffeine consumption, Y might be productivity, and Z is sleep quality. In this case, caffeine consumption does directly cause changes in productivity. However, it also, in the long term, impacts sleep quality, Z, which then impacts our productivity. So essentially, there are two paths from X to Y in our really simple DAG. We have the direct path of X causing Y, and also the indirect path of X going through Z to then cause Y. And this is an example of when we might want to differentiate between the direct and the indirect effect of caffeine on productivity. If you just wanted to know the direct effect of caffeine consumption on productivity, then you might want to control for Z, your sleep quality. However, if you want to know the entire total effect, including both direct and indirect, then maybe you don't want to condition on Z. The third type of path that's really common in DAGs is a collider. A collider looks a lot like a fork, but with the arrows pointing in the opposite direction. For a collider, we have the case where two or more variables are causing the same variable. For example, we could say X is being funny, Y is being hot, and Z is getting to date me. Or we could say X is your extracurricular quality, Y is your exam scores, and Z is whether or not you get into Chapman. We can see that for colliders, there are multiple variables that jointly cause our third variable. Now, why might this be a problem? Well, let's simulate some data. Here we're simulating that college acceptance data where we have extracurriculars and exam scores, which are completely unrelated. There's no causal path between them. And then we have acceptance, which is based on your exam scores and your extracurriculars. Acceptance is either 0 if you were not accepted or 1 if you were. Let's say we're interested in knowing whether extracurriculars help improve your exam scores. One of the ways we could look at that is we could take the data that we have and we could just do a linear regression that looks at the effect of extracurriculars on exam scores. And when we look at a model like this, we get a pretty good causal estimate of the impact of extracurriculars on exam scores. It's basically near 0. So we need to ask ourselves, can we interpret this coefficient causally? If we increase your extracurriculars, do we think that your exam scores will improve? Well, this regression coefficient suggests no, we don't think so. And because we simulated the data, we happen to know that this is the case. But what happens if we did condition on whether you are accepted to college? This happens a lot in real life by the sheer fact that oftentimes colleges, when they look at the relationships between variables, only do so based on their student population. Because, of course, they're not necessarily going to get a lot of responses if they reached out to every single student that applied to them, whether or not they were accepted. And so they just do what's convenient. They sample students that are already at the university. But conditioning your sample to only include people who were already accepted to the university can cause a problem called collider bias. If we rebuild our linear regression model, but we add acceptance as a covariate, then we can see that we get a pretty misleading coefficient for the relationship between extracurriculars and exam scores. This suggests that extracurriculars and exam scores are negatively correlated. In other words, if we increase your extracurriculars, then we would actually expect your exam scores to go down. And this is what's happening at the core of collider bias. On the left-hand side, you can see the entire population of students, and you can tell just based on the scatter plot that exam scores and extracurriculars are not related at all. They have no causal relationship. However, on the right-hand side, we've actually split our data into two groups, people who got into college and people who did not get into college. Within those groups, exam scores and extracurriculars look negatively correlated, and that's because we've basically conditioned on whether or not you got into college. For instance, think about it. When you're applying to college, you probably think that you need good grades to get in, but if you don't have great grades, maybe you can get in if you have a lot of really impressive extracurriculars. This leads to people in only this top right corner of the graph being accepted to college. You're either great in both or maybe you're great in one of them. So if we only look at the blue points on the top right, the people who got into college, it looks like extracurriculars and exam scores are negatively correlated. But if we look at the entire population, we know that that's not true. And this is the problem with collider bias. We're often controlling for variables, even if we don't realize it. Just using a sample of people who got accepted to college rather than a sample of people in general will control for whether or not you were accepted into college. For colliders, we do not want to condition on the collider Z if we want a good causal estimate of the effect of X on Y. Collider bias can also be a form of selection bias. If we only sample people who were accepted to college, that's basically the same as controlling for acceptance to college, which, if it's a collider, will induce bias in our causal estimate. So, to review, the three common paths that we see in DAGs are forks, where our third variable, the confounder Z, causes both X and Y, which might make them look associated, even though they don't have any direct causal link. We also have chains. In chains, our third variable Z is a mediator, which basically allows the relationship between X and Y to flow through it. And lastly, we have colliders. In the case of colliders, our third variable Z is caused by both X and Y. So if we condition on Z, we know something about X if we know something about Y. For forks, we often want to condition on Z in order to get a better causal estimate. For colliders, we never want to condition on a collider in order to avoid collider bias. For chains, we may or may not want to control for Z depending on whether we want the direct or indirect effect of X on Y. Some terminology that's really important when it comes to analyzing DAGs is open versus closed paths. In a DAG, an open path is a path that transmits association between two variables X and Y. Both forks and chains are open paths. They allow association to travel across those paths, making X and Y look associated. Closed paths, on the other hand, are paths that do not transmit association between X and Y. Colliders are a good example of a closed path. As long as we don't condition on the collider, we're not inducing any association between X and Y that's not there directly. Another important term is something called a backdoor path. A backdoor path in a DAG is a path that is open, but is not causal. In other words, it's a path through our DAG that might cause associations between X and Y, even though there is no causal reason for that association to exist. For instance, for a really simple case like this fork, we have a backdoor path from X to Y through Z. In order to find a backdoor path, we can ignore the direction of the arrows and just look for any path in the DAG that can take us from X to Y. And in this case, there's only one, and that's from X to Z all the way to Y. This is an open path because it transmits association from X to Y, but it's non-causal because X is not actually causing Y to happen. They're just associated through this backdoor path through Z. Our goal in DAGs is often going to be to identify backdoor paths that are causing associations that aren't causal and therefore shouldn't be part of our causal estimates, and find a way to close them. We also want to make sure that if we have a path that's not a backdoor path, we don't accidentally open it, like by conditioning on a collider. All right, to review, let's remember forks, chains, and colliders. These are all very important subgraphs that we're going to come across a lot as we analyze DAGs in order to make causal estimates. All right, that's all I have for you. I will see you next time.